Okay, guys and girls, so just a review on your mock exam. So the first question was kind of tricky, I guess. There was multiple different aspects about mechanics that you were expected to apply. So it's very important that you read the question. You've got a company that delivers packages. You've got basically a drone with a string attached to it and a package attached to that. The air is propelled down vertically with a speed of v, and the aircraft hovers motionless above the ground. So keywords coming up there: motionless, okay, or hovering. That means the velocity is 0, okay. I guess it's confused a little bit by the fact that the air is propelled downwards with a speed v, but we'll get to that in a second. Package is suspended from the aircraft on a string. The mass of the aircraft is 0.95 kilos, and the combined mass of the package and the string is 0.45 kgs. The mass of the air pushed downwards by the blades in 1 second is 1.7 kilos. So a couple of different masses going on there. Up to you to try to figure this out. State the value of the resultant force on the aircraft when hovering. So that should be the easy bit first. A quick free body diagram should show you that the force of lift is equal to the weight force, okay, since it's not moving. If it's not moving, the velocity is 0, therefore there can be no change in velocity. So that means the acceleration is 0, and that means by default that the net force is 0. Okay, on to part B then. Outlined by reference to Newton's third law, how the upward lift force on the aircraft is achieved. Okay, if you look at the mark scheme here, it says blades exert force downwards on the air. Air exerts an equal and opposite force on the blades by Newton's third law, or air exerts a reaction force on the blades by Newton's third law. Any of those will do. Personally, I would kind of, I've always liked to avoid the common version of Newton's third law, where you say you've got every action there's an equal and opposite reaction. I would try to avoid that explanation, and I would try to explain things in terms of the force felt on, say for example, the ball is equal in magnitude but opposite direction to the force felt on the foot. So you're on the ball by the foot, it's going to the right, that force is pointing this way, and the force felt on the foot by the ball is pointing back in the opposite direction. Both have an equal magnitude. So how can you apply that to this? So it might be worth thinking about this as a foot and a ball, okay? And again, I'll come back to that analogy later on in the question. So if the blade is the foot, it's pushing the air down. Now, I've drawn the air in as a little ball here because I think it helps to visualize it as just one object by itself. So with the interaction between those two objects, you've got a force pair generated. One is the force felt on the blade by the air, and obviously that's what's giving you the lift force, and then the other one is the force felt on the air by the blade, and that's the one that's pushing the air down, okay? So again, I would suggest you say something along the lines of the blades exert a downward force on the air, and the air exerts an equal but opposite in direction force on the blades. Okay, so part C was kind of tricky, I thought. Determine the velocity. State your answer to appropriate number of significant figures. So you know you're going to have to do a little bit of rounding at the end, because you'll have a point going for, 1 mark going for your sig figs. So I think here it's important to come back and reread the question, okay? So I've highlighted some of the key information here. The air above the aircraft is initially stationary. Okay, it's initially at rest. In other words, the initial velocity of the air, if you're going to treat it like a little ball, is 0. Because to be fair, they've given us a mass for this. And then the air is propelled vertically downwards with a speed v. So initially it's at rest, and then, sorry, when it's above the blade, and then it receives a pulse downwards, or a force downwards, and supposedly that force lasts for about a second or so, and it's going to come away with a final velocity of v. We are told that this ball of air has a mass of 1.7 kgs. So you can see that we've got a force, we've got a possible force that we could work out, which not too difficultly. We've got a mass, and we're asked for a velocity. So that should kind of give you the indication that this is probably going to be a momentum impulse problem. Okay. So I would first of all find the size of the force applied on the air, and the force of the applied force on the air should be the same as the lift force, because we said that from the previous part, the lift force gave us the lift force felt on the air is the same as the force felt on the blade by the air. Okay, so that means that's the lift side of it. That's the bit that comes back onto the drone, whereas that force, that same size force, is going to be the bit that's going to be pushing down on the air. So if I can work out the size of the lift, well then that should be the same size or same magnitude of force that's applied to the 1.7 kgs of air. Okay, hopefully that makes sense. So, straightforward enough. The lift force, some of the forces here in the y direction, again I've just sketched a free body diagram for that. This is the drone, of course, that I'm talking about here. But I know that the lift force that's acting on the drone is going to be the same size force that's acting on the 1.7 kilos of air. Okay. So we've got a total mass of the drone and the package and the string times gravitational field strength, and that works out to be 13.73, or roughly 14 newtons of force. That's going to be the size of the force of gravity of the drone and package combined, but also the size of the lift force that's going to be applied on the drone. And by default, if it's the size of the lift force, that means it's also the size of the force applied on the 1.7 kilos of air. So at this point I decided I was going to turn the problem sideways, just to take any vertical stuff out of the equation and just turn it into a linear momentum problem. So I've got 1.7 kilos of air here. I have a good indication this is going to be an impulse type problem. I know I have a force applied to it which is just short of 14 newtons, and the time for which the force is being applied is about 1 second. Okay, so I can bring this back to a ball and a foot situation again. We know that the initial velocity of the air was 0, and then the final velocity was v. So all I'm going to do is I'm going to sub that into my change in momentum equation there. So the force times the change in time, that's just your impulse equation, is going to be equal to the change in momentum. Of course, that is the mass times the final velocity v, which is what we've been asked to solve, minus the initial velocity, which was 0. So you sub in your numbers, and that gives me 13.7 newtons times 1 second for the duration of the collision, if you like, or explosion, times the mass is equal to the mass of the air times, well, the initial velocity was 0 anyway, so that bit falls out, and that gives you the final velocity equal to 8.0788 meters per second, or approximately 8.1 meters per second, to two significant figures. And of course that should be to two significant figures, because all of the inputs that you're given there are given to two significant figures. There's nothing tricky about the sig figs bit. Okay.